Auzubillahiminash-shaytanir-rajim. Bismillahir-Rahmanir-Rahim. Dear student, Assalamu alaikum. Today, class 10, subject physics, chapter number 12, Geometrical Optics. Topic of today's lectures are 12.9 and 12.10. And today we will cover the pages 49, 50, 51, and 52. I repeat, class 10, subject physics, chapter 12, geometrical optics. Topics of today's lecture are 12.9 and 12.10. Pages so far will cover 49, 50, 51, and 52. This is the chapter we are doing, geometrical optics, unit number 12. Today we are going to discuss power of a lens, which is on page number 49. If you open 10th class book, page number 49, you will find this topic, power of a lens. How we can, power of a lens, I repeat, power of the lens is defined as the reciprocal of its focal length. Focal length should be in meter. So how we define this is the formula of power of lens. P equals to, power of lens is denoted with letter capital P. P equals to 1 over F. We are saying this is a reciprocal. Why we are saying reciprocal? Because F is coming in the down. 1 divided by F. So F is 1 over F. That's why it is called focal length in meters, the reciprocal of focal length. So P equals to 1 over F. SI unit of power of lens is diopter. SI means System International. In System International, power of lens is diopter, is denoted with the less symbol capital D. So diopter is denoted with the symbol capital D. If F expressed in meters, so diopter will be 1 per meter. If you take, you know the length, unit of length is meter. So focal length is in meters. So if you take the meter on the top, so it will be 1 m minus 1. So 1 diopter is equal to 1 per meter square. So not 1 per meter. Thus, diopter is the power of lens whose focal length is 1 meter. Because the focal length of a convex lens is positive, therefore the power is also positive. So we were discussing lenses, convex lenses and concave lenses. So in convex lens, we know the focal length is taken as positive. We are not talking about mirrors, we are talking about lenses. So in convex lens, we have focal length is positive. So our power, which is the unit of power, is diopter. So power is also positive. But if we are considering concave lens, so focal length will be taken as negative in case of concave lens. So we discuss now power of lens. Power of lens is denoted with capital P, and capital P is equal to 1 over small f, where f is the focal length in meter. That will be taken in meter. Focal length will be taken in meter. So unit of SI unit of power of lens is diopter. So 1 diopter equals to 1 per meter. So if we have the two lenses, so one is called a convex lens and one is concave lens. If we are using convex lens, so our power will be positive, focal length will be positive, and if we are using concave lens, our focal length will be negative. Now we are going to discuss image formation by lenses. This is the topic on page number 49, the 12.9. The topic is 12.9 on page number 100, page number 49. Image formation by lens. This is the name of the topic. Mirror images are formed through reflections. Because we discussed earlier on when we started the chapter, we study the phenomena of reflection. So if we are considering the mirrors like convex mirror and concave mirror, so the reflection phenomena occurs in mirrors, but now we are studying lenses like convex lenses and concave lenses. So in lenses, the phenomena of refraction is occurring, not reflection. Refraction is occurring because whenever we are considering the mirrors, the phenomena of reflection is occurring, and whenever we are considering the lenses, the phenomena of refraction is occurring. Okay, you got to be familiarized with these two terms. So whenever we are using the mirror, the phenomena of reflection is occurring, but whenever we are using the lenses, the phenomena of refraction is occurring. Image formation in convex lens can be explained with the help of three principal rays. There are many rays of lights, but we are right now we are considering for the explanatory point of view, we are just taking only three rays of lights. Okay. One ray, first one is the ray parallel to the principal axis passes through the focal point after refraction of the lens. I told you we are discussing convex lenses and concave lenses. So the ray of light, the ray parallel to the principal axis passes through the focal point after refraction by the lens. I explain you in shortly. The ray passing through the optical center passes straight through the lens and remains undeviated. The ray passing through the focal point becomes, you can parallel to the principal axis after refraction by the lens. As I told you, this is the lens and this is the convex lens. Why this is the convex lens? We are and the phenomena of refraction is occurring, not reflection, because if we are considering the mirror, so phenomena of reflection is occurring. But since we are considering that lenses, so phenomena of refraction is occurring. So I told you I am going to take three. Madam, we are considering three rays of light: ray 1, ray 2, and ray 3. And there is an object placing in front of the lens, in front of the convex lens. So ray 1. So whenever this is the ray 1, which is parallel to the principal axis. In my earlier lecture, I told you what is the principal axis. I gave you the basic terms used in the lenses: focus, focal length, principal axis. I told you in my earlier lecture. So whenever the ray 1, which is parallel to the principal axis, whenever it passes through the lens, so it must, after passing through the lens, the phenomena of refraction is occurring. So it is meeting at a point capital F, which is called the focus point. The distance from this F to the center of the lens is noted with called focal length, and it is noted with small letter F. So this is the object which is placing in front of the lens. Whenever the ray of light which is parallel to the principal axis pass through the lens, and after passing through the lens, phenomena of refraction is occurring, and it is passing from the focus. Where the focus, there is a difference between capital F and small f. You should be very careful because there is a lot difference between capital F. Capital F is called the focus, and small f is called the focal point. So the ray of light parallel to the principal axis, after refraction, it passes through the focus point. The second ray I am considering now, which is the red one, ray 2. Ray 2 is written on it. So whenever the ray 2 is passing through the center, and it meets, it will be undeviated. It will not deviate. It will be undeviated, remain undeviated. Whenever the ray of light is passing through the C center of the lens, it remains undeviated. And the third ray, which is the blue one, it is written here, ray 3. Whenever it passes through the focus point on this side, on the left side of the lens, so after after refraction, it will meet at a point. This lens is also called the converging lens because all these rays are meeting at a point. So this image will be formed. So you can see this was the object and this is the image. So this image is formed is called the real image. The ray diagram of the this is the convex lens. Convex lens. So we are considering only 3 rays of light for our explanatory purpose. So ray 1, ray 2, and ray 2, ray 3. So next example is concave lens. So you know you are already familiar with the concave lens. So we are considering again the 3 rays: green, blue, and red rays. So this is the F point, focus point, and from focus point to the center of the mirror is called the small f, which is called the focal length. Whenever the ray parallel to the principal axis, this type of concave lens is called diverging lens because after refraction they diverge. They do not meet at a point. The rays do not meet at a point. They diverge. They scattered out. That's why this type of lens is called diverging lens or concave lens, right? So they are diverging. Here they are diverging. They are diverging, but they seems to come. They seems to be appears to be the same where the object is placed. So this is the image form. So because this is forming not on the other side of the lens, but on the same side where the object is placed, this is why this is called virtual image. But in this case, when I was talking about convex lens, so this image is formed on the other side of the lens. So this is called the real image, but this is on the same, this image is on the same where my object is placed. That's why image is called a virtual image. So we discussed about 2 lenses, convex lens and concave lens, and how the images are formed in case of convex lens and in case of concave lens. Now I am talking about image formation in convex lens. I am only taking 3 rays. For the timing, you can take multiple rays, but for the explanatory purposes, we are taking only 3 rays. The one ray which is parallel to this ray, where I am placing my cursor, the ray which is parallel to the principal axis, after refractions, they meet, they pass through the focus point and meet at a point, because this type of lens is called convex lens. Convex lens is also called the converging lens because after refraction they meet at a point. The image formed, if I place my object beyond at 2f, because f will exist here, f and 2f will exist on both sides, because in case of lenses f and 2f will be, you can see on left hand side, and f and 2f you will see on the other side of the lens as well. F mean focus, and if you double this focus, this length, this will be called 2f. 2f because from here to here is the length of focus, the length of the focus, but if you double this you will get 2f. So I'm placing my object one by one. First I place my object, this object, the brown color line you will see. So if I place my object beyond 2f, the image will be formed between f and 2f. The image will be formed between f and 2f. You can see my green line, which is on my arrow, green arrow is downward. So image will be real image. And if I place my object beyond 2f, the image will be on the other side. When the image will form, the image will be between f and 2f. The image is between f and 2f, and it will be a real image inverted. Why I am saying inverted? Because one arrow is up and the image arrow is down. That's why it is called inverted. And this image is smaller than the object. So you can see the image will be formed between f and 2f. Whenever my object is beyond 2f, so the image will be formed on the other side, f between f and 2f, and it will be real image, inverted, because the arrow is inverted or inverted. So my image will be inverted, and the object, the smaller than the object, the image will be formed smaller than the object. Next, I case the other, the object, when the object is placed at 2f. Now I am not placing my object beyond 2f, but I am placing my object on 2f. But what will happen? Same thing. On the other side, when the image will be formed, it will be formed on the 2f on the other side of the lens, convex lens. Okay, so in this case the image is at 2f. If I place my object at 2f, on the other side the image will be formed on 2f, and it will be real, inverted, and same as my object. Whatever the height of my object, the image will be of the same height if I place my object at 2f. Now the third case is when the object is placed between, when my object is placed between f and 2f. You can see object between f and 2f. My image will be formed beyond 2f on the other side. Beyond 2f on the other side, I will take again the same example, same three rays, ray 1, ray 2, and ray 3. So my image will be real. Image is beyond 2f, image will be formed beyond 2f, and my image will be real, inverted, and larger than object. You can see the image is smaller, and this is the larger image is formed. Object is smaller, and the image is larger. Now I am placing my object at f. If I place my object at f, though no image will be formed, because the reflected rays are parallel and never meet. They will never meet each other because my object is placed at f, focus point on this side, on the left hand side of the lens. So there will be no image formed. The last one, object between lens and focus. If I place my object between f and c, between the lens, so my image will be, virtual image will be formed, because the image is formed on the same side where my object, image is formed on the same side where my object is placed. So image will be bigger than the object. You can see the size of the object is smaller and the size of the image is bigger. So sorry, the image is behind the object, virtual, erect, larger than the object. Now image location by lens equation. 12.26, figure 12.26, if you consider 12.26, this is my object and this is my image is formed, and I'm taking convex lens. I'm taking convex lens, and only two rays I am considering. One ray is parallel to the principal axis, and after passing through the lens, it will be refracted and pass through the focus point f. And if my ray of light is passing through the center of the lens, it will be undeviated. It will not deviate. It will be passed through straight. It will pass through straight. It will never undeviate. And you know what is what the difference between small f and capital F? Small f is a focal length and capital F is a focus. So now I'm going to read this. Let an object OP be placed in front of convex at a distance of P. So this is OP, this is the object. OP is placed in front of lens, a convex lens at a distance. The distance from this to this lens is P, is noted with small. Object distance is noted with small p. Array P are parallel to the, this is the P and this is R, the ray. This ray PR is parallel, because this is parallel to the dotted line. You can see the dashed lines, which is this lines P. This ray is PR is parallel to the principal axis after reflection passes through focus. You know, you already know, as when we discussed this way, the ray of light parallel to the principal axis after passing through the lens, they pass through the focus point. Similarly, same thing will be happen here. So they will pass through the focus point. And then the other ray, which is this one ray, you can see the through the focus point, another ray PC. This is called P, and this is C. Axis meets the passes through the focus point. This will pass through the focus point. Another ray PC meets the ray at point P dash. You can see this is meeting at the P. This is meeting at the point ray. This midpoint at this P dash point. So after passing through the optical center C, it will be undivided. This process is repeated for other points of the objects. An inverted image O dash P dash. You can see the arrow is up and this arrow is down. This means if the one arrow is up and one the arrow is down, this is an inverted image will be formed. So O dash P dash, our OP was the object height, and O dash P dash is the image height. And image height is denoted with Q. You can see that this is the distance from this to this is called Q. Q mean image distance, or P mean object distance. Now, what is the size of the image formed? We can use the size of the image formed in the lens for a particular distance of the object from the lens. What is the nature of the image? Whether image is real or imaginary, erect or inverted. Lens formula is a tool that will be used to answer all such questions. We define lens for, you know, you have used this formula, and when we discussed mirror, I told you we will develop the formula 1 over f is equal to 1 over p plus 1 over q, where f is the focal length and p is the object distance and q is the image distance. I have already told you, and I told you when we discuss the lenses, we will use the same formula. 1 over f is equal to 1 over p plus 1 over q. This formula 1 over f is equal to 1 over p plus 1 over q holds for both, for whether it is a mirror or whether it is a lenses. It will hold true for both, whether they are mirrors or whether they are lenses. This formula will hold. 1 over f is equal to 1 over p plus 1 over q. Now we are discussing lenses, so I am using the same 1 over f is equal to 1 over p plus 1 over q. So what is saying, how can we find the size of the image, the nature of whether it is the virtual image, real image, or the distance of the object from the lens, how much? So we can use this formula. So I told you we will use this formula to find object distance, image distance, and focal length. Equation 12.4 is valid for both concave and convex lenses. Whether it is a concave lens, convex lens, for this 12.4 is valid for both convex lens or concave lens. So following signs convection should be followed while using the equation to solve problems related to lenses. You should be very, when we discuss the concave mirror, convex mirror, we'll discuss the sign conventions. So similarly, so here the things will be opposite to the mirror. In case of lenses, the things will be opposite. Focal length f is positive for converging lens. So you know convex lens is called the converging lens. So focal length will be taken as positive for converging lens, but for diverging lens, so concave lens, so our focal length will be negative. I show you now. So this is the convex lens, so our f will be positive. So in case of this is the diverging lens or concave lens, our f will be negative. This is the convex lens or we call the converging lens, f will be positive in convex lens and f will be negative for concave lens, or we say diverging lens. lens. Now, P is positive if the object is towards the left side of the lens. It is called a real object. P will be positive if P is negative if the object is on the right side of the lens. If my object is on the right hand side, so P will be negative. P is negative if the object is on the right side of the lens. It is called virtual object. If P is positive if the object is towards the left side of the lens, it is called real object. My image, this is noted with P, object distance is noted with small p, and image distance is noted with Q, and focal length is noted with small f. Now, image distance Q is positive for real image made on the right side of the lens by a real object. Q is negative for a virtual image made on the left side of the lens by a real object. So you can see when we do these examples, so you will be very much clear which one will be positive, which one will be negative. So a person 1.7 meter tall is standing 2.5 meter in front of the camera. The camera uses a convex, but we use the convex lens in the camera whose focal length is 0.05. F is 0.05. Find the image distance. We need to find out Q, the lens, and determine whether the image is real or in virtual. I told you we will use this formula 1 over F is equal to 1 over P plus 1 over Q to find whatever we need. We want to find out the Q image distance. We will use this formula to find these things. To find the image distance Q, we use the thin lens equation, which P is equal to 2.5. You know the P is object distance is 2.5 and person is standing 1.7 meter tall, is standing 2.5 in front of the camera. So our focal length is 0.05 and our P is object is 2.5 meter. I will use the formula 1 over, so I arrange the formula. I separate out 1 over Q by using the same formula. If we go back 1 over F is equal to 1 over P plus 1 over Q. Since we want to find a 1 over Q, so taking 1 over P on the other side, so it will become 1 over F minus 1 over P. So 1 over Q is equal to, I'm just putting the value, focal length is 0.05 and P is 2.5. 1 divided by 0.5, if you solve this, you will get 1 over Q is equal to 19.6, and if you take the reciprocal, it will be 0.05. The image distance is positive. You can see the Q is positive. So real image is formed, a film of the focal point of the lens. So whenever the Q is positive, it means real image is formed. You can see this is the convex lens, so I take F as positive. As I told you, F is positive for the converging lens or convex lens. Other name of convex lens is converging lens. So in this case, convex lens, so F will be positive. And Q comes positive, so it means real image is formed. So real image is formed. Next example, 12.6, which is on page number 53. So concave lens has focal length of 15 centimeter. Now you should know concave lens is negative. A concave lens has focal length of 15 centimeter. At a distance should be object from the lens be placed. So the form an image of 10 centimeter from the lens. Also find the difference of lens. Also find the magnification of the lens. This is called the magnification of the lens. Now, in this example, we need to find out the object distance and the magnification. I will use the two formulas. So one formula is same, 1 over F is equal to 1 over P plus 1 over Q. This is called the lens formula. So you want to find out P. So just take this one on this side. So 1 over minus 1 over Q. 1 over P is equal to 1 over F minus 1 over Q. So since Q is negative, because why Q is negative? Because we are using concave lens. So image will be negative, as I told you. As Q will be negative. Q will be negative. The virtual image is formed. Q will be negative. Q will be negative if the virtual image is formed. So Q, this minus 10 will be minus 10. So this minus and this minus will be positive 10. And f will be also negative because we are using the concave lens. In case of concave lens, the other name of concave lens is diverging lens. So f will be taken as negative. Okay. So these things minus plus minus. So if you take the LCM, so LCM will be 30. So take the LCM and it will come 1 over 30. Take the reciprocal. So we found P is equal to 30 centimeter. In this numerical, we want to find out the object distance and which is P and magnification. And since the formula for magnification of the lens is M is equal to Q by P, M is equal to Q by P, M is equal to Q by P. So just putting the Q is 10, we just found P. P is 30 centimeter as already given, and Q we found 10. So if you put 10 divided by 30, we get 1 by 3. I repeat this formula again. I repeat this numerical for you. A concave lens has focal length of 15 centimeter. It means focal length, since we are using concave lens, so our focal length will be negative, because I have already told you concave lens other name is diverging lens. So focal length will be negative. So at a distance should be, at what distance should be the object from the lens we place? So the form, we need to find out P. Whenever they say object distance, this will be denoted with P. So we need to find out P, and so the image is given to us 10 centimeter. Image will be taken as negative because we are using concave lens, as I have already told you. So image will be taken as negative. Image will be taken as Q is negative for the virtual image made on the left side of the lens by real object. Q and F will be negative. So I use the formula. This formula I used 1 over F. 1 over F is equal to 1 over P plus 1 over Q. So I use this formula. I just put Q is equal to, I am taking Q as negative because in concave lens Q will be as taken as negative and F will be also negative. Just plug in the values. Q is 10 and F is 15 as already given. Q is minus 10 and F is 15. Just put the values and take the LCM. You will get P equal to 30 centimeter. So another thing which we want to find out, magnification. The formula for magnification is Q by P, and Q is given to me 10 centimeter and P is 30 centimeter. 1 by 3 will be the answer. This is my magnification. Magnification is reduced to 1/3 size of the object. The image is reduced to 1/3 in size than the object. So students, this is the end of the examples 12.5, 12.6 and the topic related to properties of the lenses and sign convention on the lenses we discussed today. If you have any question regarding this topic, today's topic, please feel free to ask questions. Thank you. सुनना चाहिए इसको बनता नहीं रिकॉर्डिंग pause stop